Physical Science, Chapter 5, Thermal Energy. Thermal energy, for the big idea, is a form of energy that can be transferred as well as converted into other forms of energy. So temperature and kinetic energy. Hot water can burn your skin, right? But warm water doesn't. How is hot water different from warm water? You know that temperature of hot water is higher, and the temperature depends on the energy of the water molecules, how fast they're moving. A difference in temperature also has other effects, as you will see in the different labs that will be performed throughout this chapter. Section 1, Temperature, Thermal Energy, and Heat. Your essential questions. What exactly is temperature? If you remember earlier in the school year, we talked about temperature and heat being kind of different, right? So we're going to be talking about that. How are thermal energy and temperature related? What is the difference between thermal energy and heat? And how can you calculate changes in thermal energy? You can use the words hot and cold to describe temperature. Something is hot when its temperature is high. When you heat water on a stove, its temperature increases. The particles that make up the left burner are moving faster than the particles that make up the right burner. The thermal energy of an object is the sum of the kinetic energy and the potential energy of all of the particles that make up that object. As the butter warmed and the kinetic energy of its particles increased, the butter's thermal energy also increased. Heat is energy that is transferred between objects due to a temperature difference between those objects. Warmer objects always, highlight that please, warmer objects will always heat cooler objects, never the other way around. For example, a hot stove will heat a cold pot of water. However, a cold pot of water can never ever heat a hot stove. Just doesn't work that way. The specific heat of a material is the amount of heat needed to raise the temperature of 1 kilogram of that material by 1 degree Celsius. Scientists measure specific heat in joules per kilogram degree Celsius. When thermal energy is added to water, some of the added thermal energy has to overcome some of the attraction between the molecules before those molecules can start moving faster. In metals, electrons can move freely. When thermal energy is added, no strong attractions need to be overcome for the electrons to start moving faster. A scientist can calculate the specific heat of a material from the measurements that he or she takes from a calorimeter, such as the one shown below. To determine the specific heat of a material using calorimeter, a scientist measures the mass of a sample of the material and the mass and initial temperature of the water in the calorimeter. The scientist then heats the sample, measures the sample's temperature, and places the sample in the water in the inner chamber of this device.
Liquid nitrogen.
No, this is water. The liquid nitrogen, which is in here, will expand the bottle to the point where the bottle explodes because of pressure. This is not a combustion, like this is not a fiery explosion. This is an explosion due to pressure under the can. I added water to the bottom of the can, which will actually help this whole thing happen. Any guesses why? What do you think?
Water is room temperature, and so it will speed up the heating.
The water will speed up the process of the liquid nitrogen boiling into a gas and expanding. So if we just stuck the liquid nitrogen in there with no other thermal mass, it would take quite a while for it to get enough pressure to blow up the bottle. But by giving it that water to speed it up, then it should take maybe 20 seconds or so. Well, the can does a great job of actually forcing most of the force of the explosion upward, just like a cannon might, and then that makes the bucket, which is sitting over the top, fly up. So, at this point, I would like you guys to get behind over there.
it so hot in here? 'Cause I'm in the room. Okay, that might be a theoretical reason for the room being so hot, but there's a scientific explanation of heat that you need to know. And if you haven't learned it yet, then you're in the right place. Welcome to...
That is not a theory. She was wrong. This is a science video that has something wrong science-wise, but...
a video about heat, temperature, and thermal energy. So what is heat? Some might look at a glass of hot water and say, this glass of water contains heat, doesn't it? Actually, objects can't contain heat. However, they can contain thermal energy. In order to understand heat, we have to go through temperature and thermal energy first. So what is temperature? Temperature is the measure of how hot or cold something is compared to a reference point. A reference point is a set temperature that you can refer to, like the freezing point or boiling point of water. The temperature of the object relates to how much kinetic energy is in that object. Kinetic energy is the movement of particles in an object. Let's take this phone for example. When the phone becomes hot, the particles in the phone move faster, generating more energy. When the phone is cooling down, the particles move slower, generating less kinetic energy. There are 3 scales that are used to measure temperature: the Fahrenheit scale, the Celsius scale, and the Kelvin scale. 0K, or 0 kelvins, is absolute zero. It's the lowest temperature possible. At absolute zero, particles don't have any kinetic energy. In Celsius, it's negative 273 degrees. In Fahrenheit, it's negative 459 degrees. Fahrenheit is used by the United States, while Celsius is used by most other countries, and kelvins is used by scientists. Now let's get to thermal energy. Thermal energy is the total energy of all the particles in an object. Thermal energy depends on the temperature of an object and the number of particles in that object. The more particles an object has at a specific temperature, the more thermal energy it has. For example, which one is more thermal energy? A 1-liter cup of milk at 70 degrees or a 2-liter cup of milk at 70 degrees? The answer is the 2-liter cup of milk, because there is more milk in 2 liters compared to 1 liter, which means there's more particles in the 2-liter cup of milk. So therefore, it has more thermal energy. So let's pop the big question. What is heat? Heat is the transfer of thermal energy from a warmer object to a cooler object. The warmer object will cool down and the cooler object will warm up until both objects are the same temperature. When both objects reach the same temperature, heat stops transferring. Heat is measured in units of energy called joules. Heat can be transferred in 3 ways: convection, conduction, and radiation. Let's start with convection. Convection transfers heat only through fluids, which includes liquids and gases. For example, it could be water and air. Let's take air as our example. When air is heated, it becomes less dense, so it floats to the top.
Heat rises.
When there's cool air, it becomes more dense, so it sits at the bottom. Let's call the warm air John and
Convection currents.
the cool air Steve. Now what happens is that John starts to cool down and sinks to the bottom, while Steve starts to warm up and rise to the top. This cycle repeats over and over again, causing a convection current. Convection currents cause wind and different weather patterns. Now let's move on to conduction. Conduction transfers heat between 2 objects, so from one particle of matter to another. For example, when you heat up soup, the particles from the pot touch the particles of the soup. Since the pot is hot, the particles move faster. When it touches the soup's particles start to move faster, generating heat and making the soup hot. Last but not least, radiation. Radiation is the transfer of energy by electromagnetic waves. It also doesn't require any matter, meaning that you can feel the radiation from an object without actually touching the object. This is how we can feel heat from the sun without physically touching the sun. If a material conducts heat well, it is called a conductor. Some examples of conductors are metals and silver. This is why you might use a metal bowl to heat up something, because metal can transfer heat easily. Also, for the same reason, if you try to sit down on a metal bench outside in the summer sun, it will be really hot, because the metal has trapped in all the heat. Insulators are the opposite of conductors. They do not conduct heat well. For example, wool is used to keep warm because it is an insulator and does not transfer heat out of your body as fast as a conductor would. Another example of an insulator is plastic. If my soup is really hot, I dish the metal spoon and eat it with a plastic spoon so that I don't burn my tongue. Well, now you know everything about heat, temperature, and thermal energy.